This meeting is being recorded.
In previous sections of Chapter 12, we've seen preparation of alcohol, so how to make alcohols from other compounds. And we've also seen preparation of phenols in the last video. Now we're going to look at reactions of alcohols, and specifically how we can convert them to alkyl bromides or alkyl halides. In this first reaction here, we can see that tertiary alcohols are converted to alkyl halides using an HX. So this could be bromine, HX could be hydrochloric acid, HCl, and that would be through an SN1 mechanism. So we've added this proton transfer here to create this better leaving group, which we see here is now a water molecule. So we have our loss of leaving group followed by a nucleophilic attack from that bromide ion. And then here's our final tertiary alkyl halide product from our original tertiary alcohol that we started with. So we see that SN1, as we knew in the past, was a two-step process, and that's compared to down below primary and secondary alcohols, which can occur via a SN2 mechanism, where we have that initial proton transfer occur to protonate our alcohol. And then we have our source of bromide ions here form. And then in this single step of the substitution reaction, our bromide comes in, performs a nucleophilic attack, and at the same time, we have this loss of leaving group, which is our water molecule. So we form water in this SN2 mechanism, and we form our alkyl halide from our alcohol. So depending on your substrate, you may need to use different reagents. We are now going to form an alkyl chloride from our alcohol here. So this must be done using zinc chloride in HCl. Because this zinc cation creates a better leaving group of the hydroxide ion. So similarly to how we protonate, we can use this zinc chloride, and we can see this nucleophilic attack of our Lewis acid here. Right, that lone pair is attacking our electron deficient zinc. So now we form this intermediate, this complex here, and we have these chloride ions free, and they can now perform this nucleophilic attack, and we have the loss of this leaving group here, and this substitution occurs in a concerted mechanism here, so SN2, and we see that our alkyl halide is created. So similar to the steps involved here with a primary or secondary alcohol utilizing HBr, but we can see in this mechanism the zinc chloride acts to make that OH a better leaving group instead of protonating it. So we can also convert a hydroxyl group to a better leaving group, such as a tosyl group, using tosyl chloride and pyridine. And we use pyridine to kind of absorb the proton that is released from our alcohol, so we don't form hydrochloric acid. We keep our reaction neutral. So that's why the pyridine is required in addition to our tosyl chloride. So we have this tosylate group that has been added in place of our hydrogen here. And we can then undergo an SN2 substitution, and using something like sodium bromide here as our source of halogen. So that's what we see up top here. And we know that with SN2 mechanisms that we saw back in chapter 7, that if we have an R configuration for our starting material, we will have inversion in our product to an S configuration. So that would specifically happen, right? Since we have this chiral center here, an SN2 substitution occurs. So that's why we see that our bromine has been installed on a dash, whereas our hydroxyl group was originally on a wedge. So we saw primary and secondary alcohols react a little differently than tertiary. If we wanted to convert primary or secondary alcohols to alkyl halides, we could do that through use of thionyl chloride or this phosphorus tribromide. So we have SOCl2. Also utilizes pyridine to keep things neutral as well, so we don't have HCl forming. But we could follow this pathway and end up with a alkyl halide with a chlorine. Or we could use this reagent down here, PBr3, and through a different mechanism, we could install a bromine atom in place of that hydroxide functional group. So let's take a look at the mechanism of our thionyl chloride. So we know that the hydroxyl group is a pretty poor leaving group. So we can have this nucleophilic attack occur. And then this better leaving group is added onto our compound here. And then this pyridine is grabbing this proton here because we know that since we've already lost one of these chlorine atoms in this first step here, that we would form HCl if we didn't have it to grab it. So then we move these other electrons involved in the bond onto our oxygen. And then we see this concerted mechanism. So we have our nucleophilic attack at this carbon here. And then we have this leaving group, loss of leaving group occur. So that is how we end up with our product, our alkyl halide here, and then some byproducts as well. The PBr3 mechanism is similar in the first step. We have our bad leaving group, we have this nucleophilic attack and loss of this bromine from our PBr3. So now we've formed this good leaving group here. That free bromide ion is free to perform a nucleophilic attack. We have our loss of leaving group, right? And this is another SN2 since it's a concerted mechanism. Oh, that's what we see over here. So we have this SN2 process, our alkyl halide product, and then this HOPBr2 byproduct that results. So we did not need to use pyridine in this case because that hydrogen is absorbed in this byproduct. So our alcohols, in addition to substitution, can also undergo elimination reactions when we use the correct reagents. So we can perform an elimination in acidic conditions. So if we used heat and concentrated sulfuric acid, we can produce an alkene. So we have that elimination, and this would also produce water as a byproduct. So this is specific to tertiary alcohols, like our tert-butyl alcohol here. They follow an E1 mechanism. So it is a multi-step mechanism. It will not be concerted. But what we see here is that we protonate our alcohol to form this better leaving group. So then we have our loss of leaving group, water is removed. We have that carbocation formation, and then we have our last proton transfer and then movement of these electrons to form our pi bond here. And if we had an E1 elimination occurring, we generally would get the more highly substituted alkene. So if you recall, our Zaitsev product would be our major product with this type of elimination, and our Hoffman would result in a minor product. But if we did want to have the less substituted alkene as our product, we could initiate an E2 elimination using a strong, sterically hindered or bulky base. Something like tert butoxide potassium could be a contender. So we'll continue with our next section, 12.10, in the next video.